Hi, everyone. I hope your day is going well, but this is perhaps a good time to also remind you it's okay to get a little frustrated. It's okay to get a little mad. Technology, while wonderful, can be very frustrating sometimes. And so, certainly, that is the day that I have been having. So, this video will be posting a little bit later than 3 p.m. because I have been struggling to get it all together today. But that being said, be kind to yourself too. So let's jump right back in. We're still busy with chapter 13. And if you remember from our last class, we started talking about the sampling distribution of the proportion, sampling distribution of a sample proportion. And specifically, we talked about how the normal model can be applied in that. So we're digging a little bit deeper today and trying to make more specific when the normal model can be applied to this context of working with a sample proportion. And perhaps it's easiest to first think about when is the normal model not going to work. So let's do a very practical example here. Let's say I am doing an experiment, and in my experiment, I plan on taking a sample of 1,000 high school seniors. And in that sample, I want to know what proportion of students in the sample are taller than 6 feet 8 inches. Now, this is a very rare event, right? Most people are much shorter than 6 feet 8 inches. But we know that about 0.1% of fully grown adults do exceed that height. So when I take a sample of 1,000 high school seniors, I would expect 0.1% of them to be 6 feet 8 inches or taller. Now, that corresponds to I would expect only about one student in my sample to satisfy that criterion. So if we go through this exercise of taking a sample of 1,000 seniors, calculating the sample proportion, taking a different sample of high school seniors, calculating the sample proportion, and doing that, say, for 2,000 different samples. So 2,000 times I'm going out and taking a sample of 1,000 students, and I'm evaluating the proportion in my sample taller than 6 feet 8 inches. If I then go and draw a histogram of all the proportions that I'm observing for my 2,000 samples, you will see that the picture we end up with, this sample proportion histogram, is very much skewed to the right. It doesn't look like the bell curve is applicable here. So what exactly is going on? When are we going to end up with something that is not well approximated by a bell curve or by the normal model? Well, there are two important things that need to be considered when evaluating whether the normal model is applicable or not. Firstly, if P, and remember P is the true population proportion, if that value is very close to 0 or very close to 1, the normal model is not going to work. What does it mean if P is close to 0? That means we are dealing with rare events. Like, it is rare that someone is taller than 6 feet 8 inches. Very few people in our sample would satisfy that criterion. On the other hand, if P is close to 1, we're dealing with a ubiquitous event, right? Something that happens all the time. So either if we're working with events that are very rare, or if we're working with events that occur all the time, the normal model is questionable. We're in a much better position to use the normal model if the value for P is not too close to 0 and not too close to 1. Secondly, we need to consider our sample size, N. It's very important that the sample size is not too small. When these two considerations are taken together, what they are in combination telling us is there needs to be enough variation in a sample and enough variation between different samples before the normal model really is applicable. Because if the sample size n is small, and if p is either very close to 0 or very close to 1, then our sample is going to consist mostly of successes or is going to consist mostly of failures. Now, perhaps it's worth taking a moment here to talk about exactly what I mean by success and by failure, because I'm not saying that anyone is failing at life or is failing this class. Success is a general terminology here for a person or an object in our sample satisfying the condition of interest. So if I'm counting how many people in my sample are taller than 6 feet 8 inches, everyone who's that tall or taller, I count as a success, and everyone else I count as a failure. So failure is simply a person or an object in the sample that does not satisfy the condition of interest. So that gives you some idea of when the normal model does not work. So when does it work? Well, there are 4 conditions that we can outline, that if you can check off these 4 conditions, then you know the normal model will be either true or be really close to true, close enough that we can assume that it holds. Firstly, we need independence. Independence in this context just tells us that the data is collected in such a way that we're not sampling people who belong to the same group or cluster. Like, I'm not going out and sampling everyone who's in a basketball team, because all of those people were selected for the team based on a set of criteria, right? One individual included in the sample should not affect who else is included in the sample. That's what we mean by independence. Secondly, we need randomization. This means we're either taking a simple random sample, and we've talked about that before, or if we're looking at a treatment, it means some people are randomly assigned to receiving a treatment and other people are randomly assigned to being in a control group. But randomization needs to happen in some way. Thirdly, we talk about the 10% condition. Now, what this means is that if you look at the size of your sample, the sample size n needs to be less than 10% of the population size. If you're working with a really large population, like all people in the US or all people on the planet, you know, we're talking about hundreds of millions or maybe billions of people, then most of the time, if you are sampling 100 or 200 or even 1,000, you don't have to worry about the 10% condition. But there are instances, if you are working with a small population, then it's important to make sure that you're not sampling more than 10% of that population. And lastly, we have what we call the success-failure condition. And that means in the success group, we need at least 10 people, and in the failure group, we need at least 10 people. Now, remember here that we have defined previously p hat to be our sample proportion. So one mathematical check that you can do to see if the success-failure condition holds is you can do the multiplication sample size n times p hat, the sample proportion. That number needs to be at least 10. And also, sample size n times 1 minus p hat, that also needs to be at least 10. So these two conditions together, they help you determine whether the success-failure condition holds. And if all 4 of these conditions are true, then the normal model is a reasonable assumption when working with a sample proportion. So how does that help us? Well, let's look at a specific example. First, figure out in this example if the normal model holds, and then we'll see what kind of calculations that allows us to do. So let's say we believe that 73% of people in the US have read at least one book in the past year. And now I go and take a sample of 200 randomly selected people in the US, and in my sample, I find that 136 say they have read at least one book in the past year. Is this a situation where the normal model applies? Let's talk through those 4 conditions. Firstly, does the randomization condition hold? Well, the answer here is yes, because we are told that people were randomly selected. So that was an easy piece of information because that was stated on the outset. Next, does the 10% condition hold? Well, our sample size here is 200, but that's relative to the whole population in the US. So that is definitely much smaller than 10% of the US population, which is still in the millions. So 200 is still much smaller than 10% of the US population. Finally, we need to verify our success-failure condition. So this requires knowing what our sample proportion is. And that is simply defined as the number of times the event happens in our sample divided by the sample size. And if we evaluate this, we get 0.68 or 86%. Now, the success-failure condition now says we need to do 2 different multiplications, n times p hat and n times 1 minus p hat. So 200 times 0.68. And if you do that multiplication, you get 136. And 200 times, if you do 1 minus p hat, you'll get 0.32. And this gives us, if we do the multiplication, 64. Both of these values are larger than 10, and so our success-failure condition holds. So there we checked the 3 verifiable conditions, and all of them hold, so we can reasonably assume that, yes, the normal model will hold. So this now makes a whole avenue of calculations available to us. For example, I may be wondering, is my sample proportion unusually small? Well, I can, because the normal model holds, go and calculate a z-statistic. And when we're dealing with a sample proportion, our z-statistic is defined by this formula. P hat, which is our sample proportion, minus P, which is our population proportion, divided by sigma of P hat. And remember, that is our standard deviation. If we plug in those 3 values, we can calculate the z-score, and we can evaluate it relative to the standard normal bell curve, or the normal bell curve that is centered at 0, has a mean of 0, and a standard deviation of 1. So let's do that in this instance. We've already calculated p hat. We know that's equal to 0.68. And we know in our population, sorry, I have to scroll up here for a moment. We know in our population, 73% of people have read at least one book. So this value is 0.73. And then finally, we need to calculate that standard deviation. And you will remember from previous class, this formula is given by P times Q over N. Q is just 1 minus P. And note, this is P from the population. So this is 0.73, and 1 minus P is equal to 0.27. And finally, our sample size is 200. So if I do this calculation, 0.73 times 0.27 divided by 200, and then take square root of that quantity, I get 0.031. This now gives me everything I need to calculate that z-score. P hat minus P divided by sigma of P hat, which in this case is 0.68 minus 0.73 divided by 0.031. Again, just plug that into your calculator, and in this case, I get a value of negative 1.613. So is this value unusually small or unusually large? This is where the bell curve now becomes very useful. Right, I know I have a normal bell curve, standard normal, centered at 0, and my increments are in standard deviations of 1. And so this value that I've calculated, it's over here, like halfway between, roughly halfway between -1 and -2. So how likely am I to get a value this small? Well, I can figure that out by calculating the area to the left of that number. And this is where the normal z-score table is really useful. And so we'll spend some time working on examples in our live Zoom session looking over this. But knowing whether this value is atypical or not all comes down to what proportion of values are associated with a z-score smaller or as small as the one that we have calculated. And again, we'll really dig into that with some examples in our live Zoom session. So let's look at one more example of how we would do this calculation. Let's say we know that in the population, 13% of people are left-handed. I'm now teaching a class, and yes, for the sake of this example, we're assuming that we are meeting on campus in an auditorium where I could seat 300 people, and in that 300-seat auditorium, 25 of the desks have specifically been set up for people that are left-handed. I have a class of 135 students. I want to know what is the probability that there will not be enough seats for the left-handed students. So what do I make of this? Well, for what proportion of left-handed students will the classroom be insufficient? I know in total, I have 135 students, and if 25 or more are left-handed, then I have a problem. So what proportion does this represent? 25 of 135 is a proportion to 3 decimal places of 0.185. So how likely is it that I have this proportion or more left-handed students? Well, I can evaluate that if the normal model holds. So what are the conditions for the normal model? We need to know that we have a random sample from the population. We need to know that the 10% rule holds. So our sample, our 135 students, if we treat them as a random sample from the population of all students, again, even if we were just looking at TCU, we know we have 10,000 students at TCU. So the 135 is definitely much smaller than 10% of all students at TCU. So 10% rule holds. And finally, I want to check my success-failure condition. This is where the math comes in again. I have those two formulas, n times p hat and n times 1 minus p hat. So 135 times 0.185, that condition, or that product gives me 24.975. And sample size 135 times, if I do 1 minus the success probability, or the sample proportion, I get 0.185. Again, if I multiply that by 135, I get 110.025. But both of these values are at least 10, so success-failure condition is met. I have enough information that I can proceed applying my normal model. So if I'm now working with a normal model, what is the mean and the standard deviation of that normal model? Well, remember, the mean is always given by P, the population proportion. And in our population here, we have assumed that 13% of the population is left-handed. So our value for P is 0.13. Standard deviation, that's this sigma value, which is given by the square root of P times Q over N. So in this example, P is 0.13, Q is 1 minus that same value, which is 0.87, and our sample size is 135. So if I do this calculation, 0.13 times 0.87 divided by 135, and then take the square root of that, I get 0.029 to 3 decimals. So we are using a normal model with a mean of 0.13 and a standard deviation of 0.029. This is again very helpful because this tells you how you're actually calculating that z-score. This is the value you're subtracting from p hat. This is the value you're dividing by. So that z-score, p hat minus p divided by the sigma value, well, this is 0.185, that's our sample proportion, minus p, which is the mean of our normal model, divided by sigma, which is the standard deviation of our normal model. So if we do this calculation, then I get a z-score of 1.897. Now, remember, I'm trying to evaluate here what the probability is that I do not have enough seats in the auditorium for the left-handed students who show up, which will be the case if I have more than a proportion of 0.185. So I want to calculate the normal probability of having on this bell curve centered at P, I want to know if my P hat is 0.185, how likely am I to have more than that or a proportion larger than that? But that is equivalent to asking on a standard normal curve, one centered at 0, one where the z-table is applicable. So my standard normal curve where I can use the z-table. I've calculated a z-score of 1.897. I want to know what the area is to the right of that value. And again, we can read this from our table, and we'll dig into that in our examples tomorrow. So we want to use the Z table here to do the calculation. And that ends up telling us what proportion of students in our sample, or what the chance is that we have more students showing up for this lecture than there are seats that can accommodate left-handed students. But with that, I'm going to wrap up here for today. I know if you look at the video, you see a few more slides, but I'm pretty sure I'm already at the length I promised for these videos. So let me wrap up here, and I will see you in the live session tomorrow. I hope everyone enjoys the rest of their day.